Hello everyone, my name is Mark Lockbeeler and I'm a partner engineer at Hortonworks. Today I will be discussing the distinct value proposition Hortonworks brings to data architecture optimization. Let's quickly review the challenge faced by the company we are working with today, Megacorp. Mrs. Brady is the CIO at Megacorp and needs to expand her current 1 petabyte scale EDW infrastructure. With rapid growth in data volume, Megacorp needs to add 500 terabyte of capacity. Mrs. Brady has plans to enable analytics on all data, structured and unstructured, and she wants to lay a solid foundation for self-service BI. At an average cost of $13,000 per terabyte of EDW storage, the expansion is estimated to cost $6.5 million to add the new 500 terabyte of capacity. Megacorp is also faced with an existing data architecture that is suboptimal for 2016's projected growth. From a data storage perspective, they make decisions on a daily basis to throw away data due to escalating EDW storage costs. There are also a significant amount of low-value workloads running on their current EDW, increasing their operating costs and reducing job execution and turnaround times. And most significant is the issue of how to capture and store all of the new data sources needed for their upcoming projects. Megacorp has, we have seen, to be a very typical EDW usage pattern in the marketplace. An astonishing 70% of the data in the EDW has not been accessed in over a year. As mentioned, low-value work such as ETL jobs are consuming 55% of the overall EDW capacity, and 35% of this ETL is loading data that goes unused. ETL jobs are the largest consumer of CPU, with 5% of the ETL workloads consuming 30 to 40% of the CPU consumption throughout the day. Now that we understand the challenge we are facing, let's discuss the solution design and some supporting usage cases. The Hortonworks Data Platform, powered by Apache Hadoop, is the perfect complement to Megacorp's EDW. Adding HDP to the existing data architecture will enable Megacorp to reduce costs and optimize the value associated with their architecture. Megacorp will be able to archive data to Hadoop by moving cold or rarely used data to an active archive. They will also be able to store more data, that is, new data types and or history as an example, for a longer period of time. Hadoop can also be leveraged to enrich data for new analytic content. Moving costly ETL cycles from the EDW to Hadoop will free up expensive CPU cycles for higher value work. Let's take a look at several usage cases at actual Hortonworks customers that validate this modern data optimization approach. TrueCar moved millions of car purchases from their EDW to HDP, creating an active archive for analytic and BI users. The cost per gigabyte dropped to 23 cents, well below the $19 per gigabyte cost from other solutions. Luminar offloaded and cut its ETL processing times from 3 days to 3 hours with HDP, which enabled quicker refreshes on model development cycles with new customer transaction data. Zirmed leverages HDP to enrich new data, including pharmacy receipts, text messages, and patient web services. These are just a few usage cases which validate Megacorp's decision to modernize their data architecture with HDP. We will now turn our attention to the reference architecture we will be deploying with the quick preview of each capability and a review of how we sized our Hadoop cluster to meet Megacorp's needs. Phase 1 will focus on archiving data. The team put together a detailed architecture of the proposed solution. Data is easily accepted into HDP's flexible schema using Scoop. The data is processed and analyzed using HiveQL and Spark SQL. Then the data is made available in a real-time dashboard as well as visualization and reporting tools. Phase 2 will expand on Phase 1 by incorporating Hortonworks Dataflow powered by Apache NiFi into the architecture. New sources from data from numerous locations like server logs, application logs, XML and sensor data can be ingested. This data is easily accepted into the flexible schema of HDP using Hortonworks Dataflow and Scoop. Consistent with Phase 1, data will be available in dashboards, visualization, and reporting tools. We want to take a moment to review components leveraged in Phase 1. First, here is a sample Scoop job to load data from MySQL to Hive. As you can see, it's a very straightforward process requiring basic connection and table information. The Hortonworks Data Platform is Open Enterprise Hadoop, built on a centralized Yarn-based architecture. It supports multiple engines running in Hadoop, including a number of SQL implementations. Today we'll focus on two. The first is Apache Hive. It is the most widely used SQL engine on Hadoop. It provides a standard SQL interface to data stored in Hadoop, and users can leverage their favorite BI tool and quickly find value in raw data files. And Hadoop provides a petabyte scale for batch query execution. The Apache Hive architecture leverages the Hadoop distributed file system as its storage layer, supporting structured, unstructured, and semi-structured data. The Hive Metastore supports schema-based access to Hadoop data. The Hive Server interpreter handles compiling, optimizing, and executing query plans. And currently, the Tez and MapReduce engines offer flexible distributed engine choice. Development continues in the Hive community to accelerate BI query performance for Hive. As mentioned, it is the most widely used SQL on Hadoop engine in use today. Open Enterprise Hadoop leverages the Hortonworks Data Platform and is all about choice. And this is particularly true with SQL engines on Hadoop. The Apache Spark project provides a fast, in-memory data processing engine to the community. Spark provides elegant and expressive development APIs. It allows data workers to efficiently execute streaming, machine learning, or SQL workloads that require fast, iterative access to datasets. Apache Spark has been certified and runs on Yarn, which enables data scientists to run multiple workloads within a single shared dataset on Hadoop. Spark SQL provides a programming abstraction for distributed processing of large-scale structured data. Spark SQL users are able to leverage data frames, which are organized into named columns. Megacorp will need to consider the strengths and costs associated with both Apache Hive and Spark SQL. Apache Hive strengths include scale, maturity, comprehensive SQL, deep SQL analytics, EDW offload, and BI integration capabilities, while its weaknesses include near real-time and concurrency. While Spark SQL strengths are language integrated query, in-memory, low latency, and exploratory analytics, and its weaknesses are currently large datasets and concurrency. When considering which SQL engine to use for Phase 1, Megacorp should keep in mind the unique capabilities of Hive and Spark. Hive has a robust cost-based optimizer and mature ecosystem and is an excellent choice for ETL offloading, reporting, and large-scale aggregations. Spark SQL has a language-integrated query capability which supports exploratory analytics and dashboarding. Both tools have been evolving rapidly. We anticipate each will continue to offer more and more value to the market as new releases are delivered. Megacorp team will want to become familiar with vLine, a JDBC command line and batch-oriented Hive interface which is incredibly intuitive to use. For Embar users, there is also a Hive view which provides an interactive query editor to develop and test HiveQL queries. And Apache Zeppelin is a web-based notebook that enables interactive data analytics. It works incredibly well with HiveQL and Spark SQL, among others. When fetching data from Hive, there are a number of options that can be used in the marketplace. Here is a sample list of EDW vendor product offerings. HP Vertica SQL for Hadoop has an HCAD connector. Microsoft SQL Server 2016 offers Polybase. Oracle has Golden Gate access to Hadoop. SAP HANA has developed Smart Data Access. And Teradata offers SQL H and QueryGrid. EDWs have implemented various techniques to fetch data directly from Hadoop. Here is an example of a single SQL statement, select asterisk from mega1.car data, which, when executed with the EDW, will be transformed and executed to extract data directly from Hive. As you can see, users just need to know information about the Hive tables they want to access to fetch from Hive to their existing EDWs. Sizing is a very important state in this project. The Hadoop cluster sizing formula provided here takes into account the raw data size projected to be generated in 2016, which we will call effective capacity. We need to keep in mind that we must multiply this by several factors to obtain the Hadoop storage needed for this project. First, we must consider Hadoop storage replication factor, which defaults to 3. Keep in mind that higher replication counts impact query performance and data availability. Second, we need to consider intermediate and materialized views that we project will be needed for our project. It's hard to accurately predict the size of intermediate and materialized views at the start of a project. For this exercise, we will go with 30% additional space needed. We are going to be conservative with compression ratios and assume 3 for this project. Finally, we need to account for temporary space needs, which we will assume uses 1.2 times of capacity needs. From the original 500 terabytes projected, we're including these factors. We calculate 780 terabytes of space needed for this project. The number of worker nodes needed for Hadoop can be calculated by dividing the total space needed by the storage per server. We will assume we have 48 terabyte of storage per server, which tells us we will need 17 worker nodes for this Hadoop cluster in 2016. A Hadoop cluster is considered small if it is between 17 and 40 worker nodes. Our project will be considered a small Hadoop cluster. We will also need to dedicate between 4 to 6 nodes for master Hadoop services and 2 or more nodes for management and utility Hadoop services. Let's take a look at the layout for Megacorp. For Phase 1 at Megacorp, we will install, configure, monitor, and manage this cluster with Apache Ambari. Planning is a very important part of cluster deployment. During planning, we have determined that we will need 4 master nodes for our initial cluster, as represented on this diagram. Most HDP components have master services. This diagram was produced during our project planning phase. I do want to point out that in Phase 1, Megacorp's initial Hadoop cluster will be set up for high availability. This is why you see a similar set of services like the name node for HDFS storage represented on 2 master nodes. Also note that any HDP service highlighted in light blue will actually be started for Phase 1. Other HDP services will be installed and available for use in future phases. After we have a plan for master services for our Hadoop cluster, we need to consider which services to install on slave or worker nodes. In Megacorp's initial Hadoop cluster, we will have 17 worker nodes deployed, as represented here. Again, we will go through a planning exercise to determine which services we will install, configure, and start up for Phase 1. Note that Apache Ambari will actually guide us through a recommended configuration of Hadoop nodes, offering the flexibility to change or move services during a wizard-driven installation. And finally, we will want to plan for utility nodes for our cluster. In this case, we will deploy 2 for Phase 1. And these utility nodes will host management, client, and gateway services, as shown here. Now that we have looked at the reference architecture and sizing considerations, let's turn our attention to what will be needed to implement this plan. Jen, our project manager, pulled together a quick project plan and estimates it will take 90 days to get Ms. Brady her solution. This plan includes a workshop to kick off this project. It also involves training, build activities, testing, and promotion of the new data architecture into production. Phase 1 will involve a project manager, enterprise architect, ETL developer, and systems administrator from Megacorp. Hortonworks will provide an engagement manager, developer, and Hadoop administrator to support this project. Together, this team will deliver Phase 1. When working in the field, we hope to enable you as our partner to be able to take the role of the engagement manager, development consultant, and Hadoop architect. An education plan has also been built for this project. It will complement the existing project plan, and it will cover HDP data analytics, HDP developer, and system admin training. We also have a data scientist track available from Hortonworks University, which is not shown here. With this plan, it will enable a Megacorp to begin to support project phases as they are identified. The final component to this project that we want to review will be cost and ROI. So let's get right to it. Project costs are broken down into 4 categories. First, let's take a look at hardware and software. We have a solid estimate from past project history of $1,000 per terabyte of storage, which comes out to $500,000. Second is the consulting services we're going to use on the project. With 1,260 hours estimated at $300 per hour, this comes out to $378,000. We got this number by estimating 2 resources over a 70-day period, working 8-hour days, and an additional resource for an engagement manager at 2 hours per day over those 70 days. The next number we want to estimate into the project is training. We have 20 associates that we want to train at a unit cost of $2,500. This brings training estimate cost to $50,000. And finally, we will estimate travel and expenses at $50,000. The total for phase 1 of this project is then projected at $978,000 as indicated. If we take a look at our original cost estimate to expand the EDW, the cost was $6.5 million. And that was just hardware and EDW-based costs. Subtracting the new project phase 1 from this number, we anticipate a savings of at least $5.5 million. Thank you for joining. I hope you found this information session informative, and I hope you watched the associated demo.